Good evening, ladies and gentlemen, and welcome back to Physics Now with your host, Taylor Misiolek. Today we will be interviewing Dr. Arthur Compton, and he will be enlightening us with his research on the X-ray scatter and explaining how he has found himself awarded with the Nobel Prize in Physics. So, Dr. Compton, could you tell us a little bit about yourself and about your project? Good afternoon, my name is Arthur Compton and I was recently awarded the Nobel Prize in Physics for my work on X-ray scattering. My project set out to further define and understand beams of light referred to as X-rays. So my experiment involved directing a beam of light with a known wavelength at a plate and track the path of travel of the wavelength post-interaction. However, during that time, I noticed that the emitted wavelengths were longer than that of the incident beam's wavelength. And after some time and some research, I concluded that the incident rays were being diffracted in some way that was not really defined by classical physics at the time. And then I was able to eventually learn about Einstein's theory of quantum particles and the photon model, which defined light as not only a wave, but also a particle. And that allowed me to better understand what exactly was happening, where the photon would react or interact with an electron and cause a scattering effect as the two particles interacted. And I was able to measure that angle of scattering from the incident beam, and then I was able to develop a formula that allows for any shift to be found and determined. Well, thank you. That sounds very interesting, very enlightening as well on how you had to, face some adversary, it sounds like there. So can you tell us a little bit more about what you were trying to find? Yeah, so like I was mentioning, my experiments were not exactly lining up with the very commonly and very accepted theory of electromagnetism, which essentially would be that the incident beam would essentially radiate through the plate and have the same exiting wavelength through that plate. Obviously, I did not find that to be the case, and through Einstein's theories with quantum matter, I was able to understand that the photon was interacting with a free electron colliding, and they would act similar to billiard balls, where they would essentially scatter apart from each other. And through these experiments, I was able to prove his point that light not only can act as a wave, but also as a particle, as the emitted wavelengths of the electron and the photon were measured and interacted and responded as waves. Well, it sounds like you and Mr. Einstein were making some waves in the physics world. So where exactly did you conduct these experiments and do a lot of this research? My experiments on X-rays has been ongoing for some time. I began really looking into and studying X-rays during my free time while I was working at Westinghouse lamp company. And then just a few years later after I had started, I received a fellowship from the National Research Council, which allowed me to further my research at Cambridge University. And that was in 1919. And then within a few years, I decided to return to the U.S., where I became a professor at Washington University in St. Louis, Missouri. And from there, that's really where I was able to really refine my experiments and refine my findings. And that is where I ended up publishing my theories of X-ray scattering. Wow, a fellowship and a publishment in a few years there. Um, so do you care to tell us a little bit more about kind of that time period for you, like how everything was kind of going? Even with it being about a decade since, I'm sure it's still on everyone's mind that the Great War occurred, starting around 1914. And during that time, I was still pursuing my postgraduate studies at Princeton University. Um, and, some major events were occurring across the seas, and the US wasn't really involved until 1917, where the United States declared war on Germany. But luckily, after that, the war ended within about a year after that, and Germany signed the armistice in 1918, excuse me. And after that, a year later, again, I was moving to England to pursue my studies at Cambridge, and that was kind of when the Treaty of Versailles was emerging. And with all of the, post-war excitement and the kind of boom, things were looking up for the US, and a lot of people were excited. And even a lot of my fellow physicists were able to, get back into the world. Learning kind of erupted yet again, and academics continue to grow and become a forefront again. And a lot of us got back to work on our theories and our ideas after the war ended. Yes, it sure seems like many people have been getting back into their research after the war ended, which is very, very good. And on that note, is there anyone who you contribute, any credit to during your time? Was anyone really involved in your research as well? I was not able to do this on my own, as most scientists, physicists, chemists, are. We build upon each other's previous findings. So I couldn't be here today without the help and the work of Philip Leonard, Albert Einstein, and Max Planck during their time, and continuing through today. So Leonard's work with defining the photoelectric effect allowed Einstein to come in, add on top of that using Planck's constant, and really kind of help define that quantum level of things. And then I also really wanted to thank Charles Wilson for his work to be able to track electron recoil. He did a lot of work with his cloud chamber, and he and I are actually able to share the Nobel Prize. And he has his side with his work and discovering his method for tracking those electrons through the cloud chamber and further proving my findings. Yes, Mr. CTR Wilson did come out with some very interesting and very enlightening research with his cloud chamber. I completely understand. So with your research, what was more of the role that you had to play with the grand scheme of things? I led most of this project. I took the time. I like to be thorough with my results, and I was able to just kind of further define the kind of quantum happenings with X-ray interaction and X-ray radiation through materials. And I was able to use my knowledge and the ideas of others, such as Einstein and Planck, as I mentioned. And I was able to kind of break down the sequence of events that was occurring with the emitted wavelengths and the emitted particles that, occur with that interaction. And then my work was just kind of that final nail in the coffin to prove that aside from like the wave model and the ray model, that there are kind of there's a quantum model of light aside from just our normal everyday interaction. Yeah, it sounds like you guys were putting out some pretty groundbreaking ideas. Do you know how others in the physics community kind of took to this? So, as you probably would imagine, trying to define an entire, model of light and kind of breaking the mold for what we have known for some time doesn't always sit very well. It kind of takes some time to get used to. So even when Einstein came out with his postulates for light interaction and light being, proportional to its frequency based with, Planck's constant, it took some time. And then even with my research, it took countless experiments to fully understand and put together that the light quanta, the small particles, could explain essentially that loss of energy between the interaction of the photon and a free electron. And I had to repeat that over and over to truly define that. And not only did I define it, and I'm credited with it, but also Dutch physicist Peter de Bay also, conducted his own research. He also found similar findings to what I did. And the thing is, you can't defute facts with science. You were right there, Dr. Compton. Science, when led with facts, is non-disputable. So really appreciate all your time, and we're getting close to the end. So we'll end off with what I view as a kind of a fun question. What kind of instrumentation or apparatuses did you use to discover your findings? Yes, so I preferred to build my own apparatuses when conducting my research. And initially I had started out by making my own X-ray tubes, as well as using my own electrometer for the spectroscopy to start out. And then whenever I had gone to Cambridge, I continued to study, and it wasn't really until I started conducting my research at Washington that I began to use a Bragg spectrometer, which allowed for the emission of a specific wavelength of light that I can control and track to really understand the interaction between the wavelength, the target material, specifically the electrons, and kind of measure that scattering. Well, thank you very much. It seems like that's all we have time for today. I really appreciate you coming out to interview with us on Physics Now, and we look forward to seeing what you have to come in the future.